We start today our long journey through a great many trigonometric identities, and this page here is only the beginning. It summarizes the trigonometric identities that we already know. Of course, the most basic, the most important trigonometric identity of all of them is the Pythagorean theorem, which simply states that the sum of the squares of legs in a right triangle equals the square of the hypotenuse. If we draw the unit circle centered at the origin, and realize that for any given angle x, this distance here is cosine x, that's one leg. This distance here is sine x, that's another leg. And the hypotenuse is 1 because that's a unit circle. So by Pythagorean theorem, square of this leg, which is cosine square, plus square of this leg, which is sine squared, equals 1 squared, which is 1. These two identities simply say that cosine is an even function and sine is an odd function. We know that, along with the fact that tangent is odd, cotangent is odd, secant is even, as the reciprocal of an even function, and cosecant is also odd. These are definitions of these functions. Tangent is sine over cosine, cotangent is reciprocal of tangent, so cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. All that we know. These two identities are direct consequences of the main identity. If we take the main identity, sine squared plus cosine squared equals 1, and divide this by cosine squared, assuming it's not 0, we will get sine squared over cosine squared is tangent squared, cosine squared over cosine squared is 1, and 1 over cosine squared is by definition secant squared. That is how you get this identity. And to get the second identity, we again start with the basic identity and divide it by sine squared, assuming, of course, sine is not 0. When you divide sine squared by sine squared, you get 1. When you divide cosine squared by sine squared, you get cotangent squared. And when you divide 1 over sine squared, you get cosecant squared. That is the definition of cosecant. This is how you get the second of these identities. Let's recall real quick how we, for instance, know that cotangent is odd. Why is cotangent odd? Well, cotangent, remember, is defined as cosine over sine. So cotangent of negative x is cosine of negative x over sine of negative x. And now we, of course, use the fact that cosine is even and sine is odd. The sine function is odd. And in this fraction, we get negative cosine over sine, which is, of course, negative cotangent x. So cotangent is indeed odd. Now we get these 6 co-function identities. And let's briefly remind ourselves how we get them. If I draw a right angle triangle, and say this angle is x, the opposite leg is a, the adjacent leg is b, by the Pythagorean theorem, the hypotenuse c is simply root a squared plus b squared. And here we have sine x is a over c. Then the other acute angle is, of course, pi over 2 minus x. That is because the three of them, pi over 2x, and the third angle must add up to pi. And so if one angle is pi over 2, a second angle is x, the third angle must necessarily be pi over 2 minus x. So in this triangle, sine is a over c, opposite leg over the hypotenuse, but at the same time, this ratio, a over c, with respect to this angle, is adjacent leg over hypotenuse. So a over c is also cosine of pi over 2 minus x. That is how we, for instance, get this identity. All other identities are obtained the same way. This identity can be obtained from the same triangle. Sine of pi over 2 minus x is, in this right triangle, b over c, opposite leg over the hypotenuse. But at the same time, with respect to angle x, b over c is adjacent leg over hypotenuse. So b over c is also cosine x. That is the second identity. And so on. You can easily get the other 4 identities the same way. Let's practice these formulas and solve 2 examples. In this first example, we need to express 1 minus sine x over 1 plus sine x minus 1 plus sine x over 1 minus sine x in terms of tangent and secant. So let me add a page here. Express in terms of tangent x and secant x. All right, the first step, which seems reasonable, is to bring the two fractions to a common denominator. So the common denominator is, of course, the product of the denominators. This should be sine x. So 1 plus sine x, 1 minus sine x, and in the numerator then will be 1 minus sine x times 1 minus sine x minus 1 plus sine x times 1 plus sine x. So what happened? We brought to a common denominator both fractions. Now if we expand the squares in the numerator, that simply is, or rather let's write it just as a square first, 1 minus sine x squared minus 1 plus sine x squared over the denominator, where we can use the formula a plus b, a minus b equals a squared minus b squared. So I can write the denominator as 1 squared minus sine squared. Now in the numerator I expand both squares, so it'll be 1 minus twice the product plus square of sine, 1 plus twice the product plus square of sine. Now in the denominator I can replace 1 minus sine squared by cosine squared. That is because sine squared and cosine squared add up to 1. So if I expand the parentheses, it'll be 1 minus 2 sine x plus sine squared x minus 1 minus 2 sine x minus sine squared x over cosine squared x. Now combining the like terms, we see that sine squared and negative sine squared cancel out. 1 and negative 1 also cancel out. And I get negative 2 sine x and negative 2 sine x, which is negative 4 sine x. Now, to express this through tangent and secant, I can write this as negative 4 times sine over cosine, which of course is tangent, times 1 over another cosine, which of course is secant. So the whole thing then becomes negative 4 tangent x secant x. All right, and the second problem there was to verify a couple of identities. So let me write it here. Cosine squared minus tangent squared equals 2 minus sine squared minus secant squared. So my first desire is to rewrite tangent and secant as fractions through sine and cosine. So that'll be cosine squared x minus sine squared x over cosine squared x equals 2 minus sine squared x minus 1 over cosine squared x. Let's clear the denominators. Of course, we assume here that cosine is not 0. So if we multiply through by the denominator cosine squared x, we get cosine to the fourth power of x minus sine squared equals 2 cosine squared minus sine squared cosine squared minus 1. Now it seems reasonable to replace 1 by sine squared plus cosine squared. So that'll give me cosine to the fourth x minus sine squared x equals 2 cosine squared x minus sine squared x cosine squared x minus cosine squared plus sine squared. Now if we expand the parentheses, distribute the minus, this here will be a minus. And negative sine squared and negative sine squared cancel out. Also, 2 cosine squared minus cosine squared combine, and so we get cosine to the fourth x equals cosine squared x minus sine squared x cosine squared x. Now factor out cosine squared x. On the right. That'll give us cosine to the fourth x equals cosine squared x times 1 minus sine squared x. And of course, now we simply replace 1 minus sine squared x by cosine squared x. And we realize that on both sides we have cosine to the fourth of x equals cosine to the fourth of x, which is indeed a right equality, a right identity. So this finishes the first one of these two examples. In the second example, we need to make a small correction. It's not really a mistake, it's just that we haven't yet talked about the formula about cosine of a double angle. So I want to add here that cosine of 2x really is cosine squared minus sine squared. So we are actually checking that this simplifies to this. So let me add a page. And we are verifying the identity. Secant squared of negative x minus tangent squared x over tangent x times 2 plus 2 tangent x over 2 plus 2 cotangent x minus 2 sine squared x allegedly equals cosine squared x minus sine squared x. Well, first of all, by the fact that secant is even, I can get rid of the minus here and put a plus. Now the next step is to write all these functions, secant, tangent, 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 and cotangent, as ratios. So secant is 1 over cosine squared, tangent squared is sine squared over cosine squared, tangent is sine over cosine. Here we have sine over cosine, and here we have cosine over sine. Minus 2 sine squared x allegedly equals cosine squared minus sine squared. Here, in the first fraction, let's multiply both the numerator and denominator by cosine squared x. Of course, when you have a fraction a over b, and you multiply and divide the numerator and denominator by a non-zero constant, you get the same fraction. Of course, here cosine is not zero. To simplify the second fraction, let's multiply the top and the bottom by sine times cosine. So what will happen? When we multiply this by cosine squared, we'll get simply 1. Here we'll get simply sine squared. Here, when we multiply sine over cosine by cosine squared, we'll get sine times cosine. Each term in this fraction is multiplied by the product, sine times cosine. So we're going to get 2 sine x cosine x plus 2 sine x times sine x over 2 sine x cosine x plus 2 all right. 2 cosine x cosine x. We should have done that immediately. We can get rid of the 2's. There's no need to carry them around. The rest of the expressions stay as they are. So here, of course, I'd like to replace 1 minus sine squared by cosine squared. And now when I divide cosine squared by cosine x, I will get cosine by sine. So that gives me cosine over sine. And here, I very much want to factor out sine x in the top and cosine x in the bottom. If I factor out sine x in the top, I get sine x times cosine plus sine. And in the bottom, I will get, factoring out cosine x, sine plus cosine in parentheses, which is very convenient because I can probably cancel by sine plus cosine. We'll think about it. Can sine plus cosine be 0 here, but not 0 here? Probably not, because if we have sine plus cosine 0, either sine or cosine are not 0. They cannot be both 0. If, for instance, cosine is not 0, they cannot be both 0 because their squares must add up to 1. If cosine is not 0, dividing by cosine in this equation, we get sine over cosine, which is tangent. Cosine over cosine is 1. We get tangent x plus 1 equals 0. So tangent equals negative 1. And if sine is not 0, one of them has to be non-zero. We can divide this equation through by sine. Sine over sine equals 1. Cosine over sine equals cotangent. And therefore, 1 plus cotangent equals 0. That is not possible because that implies that 2 plus 2 cotangent x is 0. And that is in the denominator. So we must have that 1 plus cotangent x is not 0, because 1 plus cotangent x is in the denominator. But that is 1 plus cosine over sine is not 0. So in particular, sine x is not 0. We can multiply this by sine x to get that sine x plus cosine x is not 0, and sine x is not 0. So no, this answers my question. Sine x plus cosine x cannot be 0. That is the requirement of existence of the original identity. The fact that we have 2 plus 2 cotangent x in the denominator implies that sine x plus cosine x is not 0. So it's safe to divide. Of course, sine x and cosine x are not 0 either, because they're involved in tangent and cotangent. So in fact, this whole thing, product of two fractions, is 1. I simply get 1 minus 2 sine squared x equals cosine squared x minus sine squared x. And that is certainly true if we replace cosine squared by 1 minus sine squared x. Because then we'll have 1 minus 2 sine squared x equals 1 minus sine squared x minus sine squared x. And so now we have equality of the left-hand side and equality of the right-hand side. And so all of these question marks are actually check marks. So this verifies the second identity on the first page. And the second problem here is now finished. The next set of identities is the so-called sum and difference identities, of which the most important one, from which we will derive everything else, is the cosine of a difference formula. So cosine of alpha minus beta is product of cosines of the two arguments plus product of sines of the two arguments. From this one, we will derive cosine of the sum, cosine of the sum and sine of a difference, and tangent of sum and difference. So how do we derive this formula? Not surprisingly, we will derive it using the unit circle. And in my picture, both angles alpha and beta will be in the first quadrant, although that's of course not necessary and the explanation remains valid, even if alpha and beta are not in the first quadrant. So let's say alpha here is this angle and beta is this angle. So that this measures to alpha minus beta, this being alpha, this being beta, so the leftover is the difference, alpha minus beta. We can also measure the angle alpha minus beta directly from the positive direction of the x-axis. Let's say it's here. Let's say this point is A, this point is B, this point is C, and this point is D. What are the coordinates of these points? The coordinates of A are cosine alpha, sine alpha. The coordinates of B are cosine beta, sine beta. The coordinates of C are cosine alpha minus beta, sine alpha minus beta. That is because point C corresponds to angle alpha minus beta. And of course, D has coordinates 1, 0. So the idea behind this computation is the following. Note that triangles AOB and triangle COD are equal. Why is that? Well, that is because both are isosceles triangles in which OA equals OB equals OC equals OD equals 1, and also the angles between equal sides. AOB equals angle COD equals alpha minus beta. By equality of these two triangles, we conclude that distance AB equals distance CD. We are going to express these distances, AB and CD, through the coordinates. We will need to recall one fact that I hope you know from your previous math classes. How do we compute? How do we express the distance between 2 points given by their coordinates? The distance between points AB and CD is given by the square root of the sum of squares of differences, first coordinates and second coordinates. If you're a little rusty onto where this comes from, we can quickly remind ourselves how this formula is obtained. Say we have a coordinate plane, 2 points, AB and CD, and this here is the distance between them. By the Pythagorean theorem, I can view this distance as the hypotenuse in this right triangle, in which one leg is the absolute value of the difference of the x-coordinate. So this here is the absolute value of a minus c, or c minus a, which is the same. We don't really know. We can't say that this is c minus a, because we don't know which point is to the right of which. We don't know that c minus a is positive. So the proper way to write this is using the absolute value. Much the same way, we don't know whether b is greater than d or d is greater than b. So the other leg is the absolute value of b minus d. So by the Pythagorean theorem, this distance d squared as the square of the hypotenuse equals sum of the squares of legs, a minus c squared plus b minus d squared. Of course, when you square the absolute value, you can drop it, because it's non-negative anyway. And from here, d is the positive square root of a minus c squared, b minus d squared. All right, now we already said that a, b, and cd are equal distances. To avoid having to work with square roots, we're going to compute squares of these distances. Of course, the fact that A, B, and CD are equal implies that their squares are equal. And we're going to compute the squares of these two things. AB squared, for example, is sum of squares of difference of coordinates. X coordinates, so it's cosine B minus cosine alpha, or cosine alpha minus cosine B, which is the same. And the same with the Y coordinates, sine alpha minus sine beta. And same for CD. CD squared is sum of the squares of two things. Difference of the x coordinates, cosine of alpha minus beta, and 1. And sine alpha minus beta and 0. Now, because AB and CD squared, because the squares of AB and CD are equal, these things must be equal. So we're now going to equate this and this. Equating them, we get cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared equals cosine alpha minus beta squared, cosine alpha minus beta minus 1 squared plus sine squared of alpha minus beta. All right, let us open all parentheses. So this first square is, for instance, square of the first guy, square plus square of the second guy, minus twice their product. Same with the second term, square of the first guy plus square of the second guy minus twice their product. That is sine alpha minus sine beta squared. And the same thing on the other side. Square of the first guy plus square of the second guy minus twice their product. Sine squared alpha minus beta. Now, we should identify some of the squares of sine and cosine of the same argument. This is cosine squared, and this is sine squared, and they add up to 1. Same here. Cosine squared and sine squared add up to 1. And finally, cosine squared beta and sine squared beta add up to 1. So we have two ones here, and we have two ones on the other side. So everything circled cancels. Because again, cosine squared and sine squared of alpha add up to 1, cancel with this one. And now cosine squared beta and sine squared beta add up to 1, and so do cosine squared and sine squared of alpha minus beta. So what is left is negative 2 cosine alpha cosine beta, negative 2 sine alpha sine beta equals negative 2 cosine of alpha minus beta. Upon canceling by negative 2, we get cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta, as claimed. That is a very important formula. We'll use it all the time. And this formula gives rise to the other sum and difference formulas on the next page. How do we, for instance, deal with cosine of a sum? Well, we simply write cosine of a sum as difference alpha minus negative beta. And at this point, we use the cosine of a difference formula from the previous page. According to that formula, cosine of a difference is cos alpha cos negative beta plus sine alpha sine negative beta. Now we again recall that cosine is even. That means cosine negative beta is simply cosine beta, and sine is odd. Sine of negative beta is negative sine beta. So using this fact, we can write the last line as cosine alpha, cosine beta. So we simply ignore the negative sign here, and the negative sign here goes up front, giving us negative sine alpha, sine beta. As claimed. How do we deal with these two formulas, sine alpha plus beta, sine alpha minus beta? Well, using the co-function identity, every sine can be expressed as a cosine, because sine of alpha plus beta is nothing but cosine of pi over 2 minus alpha plus beta. That is a co-function identity. now apply the cosine of a sum formula, or cosine of a difference. Cosine of a difference, again, is cosine pi over 2 times cosine of the other guy, alpha plus beta, plus, remember there's a plus here, sine pi over 2 sine alpha plus beta. And we haven't really proved anything because we just proved that sine alpha plus beta equals sine alpha plus beta. Cosine pi over 2 is 0, sine pi over 2 is 1, so we proved that x equals x. Well, that is a question for everyone. How do we use the formulas that we have to prove the sum and difference formulas for the sine function? Apparently the co-function identity doesn't work, so we might use an argument similar to the one we used for cosine of a difference, alpha and beta. Think about it. We might get back to this question later. But what about tangent, though? If we believe into these two formulas, what about the tangent of a sum and difference? Well, the argument is, of course, by definition of tangent. Tangent of alpha plus beta is sine of alpha plus beta over cosine of alpha plus beta. And sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta, cosine alpha cosine beta minus sine alpha sine beta. What happened was we used the definition of tangent, and here we use the some formulas for sine and cosine. We have them both above. Now, the idea is to divide each term of this fraction by the product cosine alpha times cosine beta, assuming, of course, it's not 0. Right? So if we divide each term by cosine alpha cosine beta, we need to, of course, assume that they're not zero. Now, what cancels here? We have cosine beta and cosine beta canceling, and then sine alpha over cosine alpha. That's tangent alpha. Here we have cosine alpha and cosine alpha canceling, and sine beta over cosine beta is tangent beta. Here this simplifies to 1, and sine alpha over cosine alpha simplifies to tangent alpha, and sine beta over cosine beta is tangent beta. And so we end up with tangent alpha plus tangent beta over 1 minus, note the minus sign, tangent alpha, tangent beta. Now, what would happen if we had a minus sign here? We would have sine of a difference and cosine of a difference. And here we would have not sums but difference formulas. So sine of a difference makes a minus here. Cosine of a difference makes a positive sign here. So this would be minus, this would be a plus, and so this would be a minus, and this would be a plus. So we have now proved the sum and difference formulas for the tangent function. I would now like to get back to the formulas concerning the sine function and try to actually obtain an explanation that works. This one that I was trying to give here did not work. So the explanation that I will try to implement will involve the basic identity. We know that sine squared x plus cosine squared x is 1 for any real x. And so, for this reason, sine squared is, of course, 1 minus cosine squared. And I will, instead of x, write alpha minus beta here, and then use the difference formula for cosine. So sine squared of alpha minus beta equals 1 minus cosine squared alpha minus beta. And now I'm applying the difference formula for cosine. According to which we have cosine of alpha minus beta as cosine alpha cosine beta plus sine alpha sine beta. All that is now squared. Now, in the next step, we will expand this square, and I would like also to replace 1 by cosine squared and plus sine squared. So that'll be cosine squared plus sine squared, that is 1, of alpha minus this thing squared. So square of the first guy. Cosine alpha, cosine beta, both squared. Plus square of the second guy. Sine alpha, sine beta, both squared. Plus twice their product. Sine alpha, cosine alpha, sine beta, cosine beta. Now we of course distribute the minus. Let's do that. Now, let's factor out cosine squared alpha from here and here, and likewise sine squared alpha from here and here. And this term we will leave unchanged. So when we factor out cosine squared alpha, in parentheses we get 1 minus cosine squared beta. And for the green terms, we get sine squared alpha times 1 minus sine squared beta. Now, of course, we can replace 1 minus cosine squared beta by sine squared beta, and 1 minus sine squared beta we can replace by cosine squared beta. All right. Now I would like to write this last term as twice that term because of the factor 2 in front of it. I will simply copy and paste that. Erase 2 in front of it. And copy and paste the last term. Now, let's factor out cosine alpha sine beta from this term and from this term, and sine alpha cosine beta from the remaining two terms. So in parentheses, we will get cosine alpha sine beta minus sine alpha cosine beta from here. And for the green terms, when we factor out sine alpha cosine beta, in parentheses we will get sine alpha cosine beta minus cosine alpha sine beta. Now, interestingly enough, the expressions in parentheses are only different by a sign. So I can factor out them. Sine alpha cosine beta minus cosine alpha sine beta. What is now in parentheses is sine alpha cosine beta minus cosine alpha sine beta, which of course is just sine alpha cosine beta minus cosine alpha sine beta squared. And so what we have obtained is that sine squared of alpha minus beta equals the square of sine alpha cosine beta minus cosine alpha sine beta. From here, of course, since the two squares are equal, we get that sine of alpha minus beta is plus minus. We'll need to discuss which sign it is, of sine alpha cosine beta minus cosine alpha sine beta. So should it be plus or minus? Well, let's try beta to be 0. Suppose alpha is arbitrary. And beta is 0. What will we get? We get sine alpha minus 0, which is of course sine alpha, equals plus minus sine alpha cosine 0 minus cosine alpha sine 0. Sine of 0 is of course 0, so that is plus minus, and cosine of 0 is 1, plus minus sine alpha. Well, in order for sine alpha to be equal to this for an arbitrary alpha, we have to have the positive sign here. So finally we get our formula as sine of alpha minus beta equals positive sine alpha cosine beta minus cosine alpha sine beta. That is the sign of a difference formula. Now, to get the sign of a sum formula, we simply write a sum as a difference. Sine of alpha plus beta can be written as sine of alpha minus negative beta. And applying the just derived formula that gives us sine alpha cosine of negative beta minus cosine alpha sine of negative beta. Now, using the fact that cosine is even, and so cosine of negative beta is simply cosine beta, and sine is odd. So sine of negative beta simply is negative sine beta. Our formula becomes sine alpha cosine beta plus cosine alpha sine beta. And so the sign of a sum formula is sine of alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. That is the sign of a sum formula. All right, so now we have all of these formulas done. We have proved them, we have properly explained them. And what's left to do now is to look at some computational examples on the next page. In the first of these examples, we need to express cosine of 75 degrees and sine of 15 degrees through radicals. So the idea is, of course, the following. We simply need to write cosine of 75 degrees as cosine of 45 degrees plus 30 degrees. The idea is that we know all trigonometric functions of 45 degrees and 30 degrees, and we can express the cosine of the sum through these known trigonometric functions. So cosine of a sum, as we know, is product of cosines minus product of sines. Cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Now cosine of 45 degrees is root 2 over 2, cosine of 30 degrees is root 3 over 6, root 3 over 2, excuse me. Sine 45 degrees is root 2 over 2, and sine 30 degrees is 1/2. So this simply is root 6 minus root 2 over 4. And for sine of 15 degrees, we can argue that 15 is 45 minus 30. And we again know all trigonometric functions for 45 degrees and 30 degrees. So now we use the sine of a difference formula. Remember, sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. And so this here becomes root 2 over 2. Cosine of 30 degrees is root 3 over 2. Cosine 45 degrees is root 2 over 2. Sine 30 degrees is 1/2. And we again get root 6 minus root 2 over 4. You may be wondering why these things are equal. You can of course recognize that this is simply a co-function identity, because 75 degrees is 90 minus 15 degrees, and that by the co-function identity is sine of 15 degrees. So of course it's not a coincidence that these two values are equal. So this example is over, and let's look at a more interesting example, where we need to compute sine of arcsine of 1/2 plus arcsine of 3/5. Well, first of all, we apply the sine of a sum formula. So sine of this sum if you call this alpha and this beta, I can write this as sine of alpha plus beta. And that we know is sine of alpha cosine beta plus cosine alpha sine beta. And what we need to do now is compute all these four numbers: sine alpha, cosine beta, cosine alpha, and sine beta. What is sine alpha? Sine alpha is sine of arc cosine of 1/2. Well, we know what to do. We know this number will be positive because our cosine of 1/2, which we call alpha, is in 0 pi. So that's quadrant 1 or 2. And sine there is non-negative. So when we replace sine by square root, 1 minus cosine squared, we know we need to take the positive sign. And now this is 1 minus cosine of arc cosine of 1/2 is simply 1/2. So this here is root of 3/4, which is root 3 over 2. Now, cosine beta is cosine of arc sine of 3/5. And arc sine of 3/5, which we call beta, by definition of arc sine, belongs to the interval negative pi over 2 pi over 2, and therefore this is quadrant 1 or quadrant 4, and cosine there is non-negative. So when we replace cosine by plus minus square root of 1 minus sine squared, we know we need to take the positive square root. Now, of course, sine of arc sine of 3/5 is 3/5. So this here is root of 16 over 25, and that is 4 over 5. Now, cosine alpha is cosine of arc cosine of 1/2, and that is 1/2. And sine beta is sine of arc sine of 3/5, and that is simply 3/5. So we can continue this line here. Sine alpha is root 3 over 2. Cosine beta is 4 over 5. Cosine alpha is 1/2. And sine beta is 3/5. So this will be 4 root 3 plus 3 over 10. It's also nice to check that this number actually is less or equal than 1, definitely positive. Just to know, it's sine of something. One good verification whether our answer makes sense is to check that this number is less or equal than 1. That is equivalent to 4 root 3 plus 3 being less or equal than 10. That is equivalent to 4 root 3 being less or equal than 7. That is equivalent to 16 times 3, which is square of 4 root 3, being less or equal than 49, which is square of 7. And that is indeed true. 49 is less than 40, 48 is less than 49. This number is close to 1, but it's definitely less or equal than 1. If this number were greater than 1, we would know our answer was wrong. Sine cannot take values more than 1. So this example is over. We can switch to the next example. So here we need to compute sine of alpha plus beta, cosine of alpha plus beta, and tangent of the difference. If we know sine alpha and know that alpha is in the first quadrant, we know cosine beta, and we know that beta is in the third quadrant. So if we want to compute sine of alpha plus beta by the sign of a sum formula, that is sine alpha cosine beta plus cosine alpha sine beta. Now sine alpha we know, and cosine beta we know. We need to compute cosine alpha and sine beta. Well, sine alpha, by the basic trigonometric identity, or otherwise Pythagorean theorem, is plus minus square root of 1 minus cosine squared. Excuse me, that is cosine alpha. Cosine alpha is plus minus root 1 minus sine squared. And because alpha is between 0 and pi over 2, we know we need to take the positive sign. This is the first quadrant. So this is 1 minus 3/5 squared. That's 1 minus 9 over 25. That's 16 over 25. And square root of that is 4 over 5. Now for sine beta, we again use the Pythagorean theorem. That's plus minus square root 1 minus cosine squared. That is, of course, beta. And beta is in between pi and 3 pi over 2. So sine beta is negative. That is quadrant 3. So we know we need to take the negative sign. It will be negative 1 minus negative 5 over 13 squared. So that's 25 over 169. One minus 25 over 169. 169 minus 25 is 144. And square root of that is 12 over 13. So our computation here is 3/5 times negative 5 over 13 plus 4/5 times negative 12 over 13. So 5 and 5 here cancel out. We get negative 3 over 13 minus 4 times 12 is 48, and 5 times 13 is 65. And of course, the common denominator is 65. By 13, that's 5. Negative 15 minus 48. That's negative 63 over 65. In the interval negative 1, 1, by the way. So it might be correct. Now when we compute cosine of the sum, we again use one of the formulas we proved before, cosine of a sum. That's cosine, that's product of cosines minus product of sines. All these values, I believe we already know. Cosine alpha, cosine beta, sine alpha and sine beta. So cosine alpha is 4 over 5. Cosine beta is negative 5 over 13. Sine alpha is 3 over 5, and sine beta is negative 12 over 13. So we get negative 4 over 13 plus 36 over 65. The common denominator is 65 over 13, that's 5, negative 20 plus 36, that is 16 over 65. I would also do a small verification here, that sine alpha plus beta plus cosine squared alpha plus beta add up to 1. Might be a little tedious, but it's worth doing that. So we are checking whether negative 63 over 65 squared plus 16 over 65 squared equals 1. Now, 16 squared is 256, 63 squared is 4969. So 4969 plus 256 is 5,225, and what's left to do is compute square of 65. All right, let's check this computation. Yes, this of course needs to be 3. And so this will be 4. And so we do get 4225 in both cases, so this identity checks. That was very important. All right, what about tangent of the difference? Tangent of alpha minus beta. Remember, the formula is tangent alpha minus tangent beta, 1 plus the product of tangents. So we need to compute tangent alpha and tangent beta. Well, that's easy. Tangent alpha is sine alpha over cosine alpha. Sine alpha we know is 3/5. Cosine alpha we know is 4/5. So tangent is 3/4. Tangent beta is sine beta over cosine beta, and that is negative 12 over 13 over cosine beta, which is negative 5 over 13. That's 12 over 5. So in the formula we get 3/4 minus 12 over 5 over 1 plus 3/4 times 12 over 5. So if we multiply the top and the bottom by 4 times 5, by 20, we get 3 times 5 minus 12 times 4 over 20 plus 3 times 12 is 36. That is 15 minus 48 over 56, and 15 minus 48, that is negative 33. Negative 33 over 56. I think the fraction is irreducible. 33 is 3 times 11, and 56 is 7 times 8. Yeah, so they're all co-prime. Well, that is then the answer, and this finishes this example. The next 3 sets of trigonometric identities are double angle, half angle, and reduction formulas. Let's first talk about double angle formulas. These allow us to express trigonometric functions of double angle to alpha over or through trigonometric functions of single angle alpha. They are easily provable using the summation formulas we know from before. For example, to prove the first formula for sine of 2 alpha, we simply represent 2 alpha as alpha plus alpha, and now apply the sine of a sum formula. So that'll be sine alpha cosine alpha plus cosine of the second argument sine of the first argument, which is of course 2 sine alpha cosine alpha. That is a very useful formula, simple but useful. For cosine of the double of 2 alpha, the second formula, cosine of a double argument, we likewise write 2 alpha as alpha plus alpha and apply the cosine of a sum formula. So that'll be cos minus sine And of course, that's cosine squared minus sine squared, as claimed. And likewise for tangent of 2 alpha, writing 2 alpha as alpha plus alpha, and applying the tangent of a sum formula. We get that this is tangent alpha plus tangent alpha over 1 minus tangent alpha times tangent alpha, and that is of course 2 tangent alpha over 1 minus tangent squared. I recommend that you memorize all three formulas because they are very common. They're used as the basis for proving reduction formulas. The reduction formulas are so called because they allow you to express squares of trigonometric functions through trigonometric functions not involving squares. You lower the powers at the price of raising the argument. So how do we prove these formulas? Well, for the first formula, we will start with the right-hand side and recall the basic trigonometric identity, the most important of all of them. That is sine squared plus cosine squared of the same argument equals 1. And the other identity that we will use here is the one we just proved, cosine of a double angle, that cosine of 2x equals cosine squared x minus sine squared x. So now if we take the right-hand side, 1 minus cosine of 2 alpha over 2, and write 1 as cosine squared alpha plus sine squared alpha. That is just 1. And replace cosine of 2 alpha by cosine squared alpha minus sine squared alpha. Distribute the minus. We get cosine squared plus sine squared minus cosine squared plus sine squared. Combine the like terms. Cosine squared and negative cosine squared cancel out. Sine squared plus sine squared gives you 2 sine squared. And over 2, that simply gives you sine squared alpha. That proves the first formula. For the second formula, the argument is very similar. We take 1 plus cosine of 2 alpha, and again apply the same two identities, writing 1 as cosine squared plus sine squared. And cosine of 2 alpha as cosine squared minus sine squared. Distributing the minus gives us cosine squared alpha plus sine squared alpha minus cosine squared alpha plus sine squared alpha. This should here be a plus, so we're distributing a plus. So this is a plus and this is a minus. This time sine squared cancel out, and cosine squared alpha combines to give us 2 cosine squared alpha over 2. So that is cosine squared alpha. So that proves the second formula. For the third formula, we start with the right-hand side, 1 minus cosine of 2 alpha, 1 plus cosine of 2 alpha. Using the same two identities, we write 1 is cosine squared alpha plus sine squared alpha. And cosine 2 alpha is cosine squared alpha minus sine squared alpha. And in the denominator, again, writing 1 as cosine squared alpha plus sine squared alpha. And cosine 2 alpha is cosine squared minus sine squared. Distributing, we get cosine squared alpha plus sine squared alpha minus cosine squared alpha plus sine squared alpha. And in the denominator, cosine squared alpha plus sine squared alpha plus cosine squared alpha minus sine squared alpha. In the numerator, cosine squared and negative cosine squared cancel out. In the denominator, sine squared and negative sine squared cancel out. On top of that, we have sine squared alpha, like terms in the numerator, and the like terms in the denominator are cosine squared alpha. So this here becomes 2 sine squared alpha over 2 cosine squared alpha, which I can of course write as sine alpha over cosine alpha squared, and that is simply tangent squared alpha. So that proves the third formula. These formulas are very useful when in calculus you get to integration, to integrate sine squared or cosine squared. It's very convenient to use these formulas. Another consequence of double angle formulas is the half angle formulas. We can express half angles of sine, cosine, and tangent. I mean sine, cosine, and tangent of half angles using radicals. And these follow directly from the formulas on the previous page. For instance, we have sine squared alpha equals 1 minus cosine of 2 alpha over 2. Note that this is always a non-negative number, of course, and therefore sine alpha equals plus minus square root of 1 minus cosine of 2 alpha over 2. And replacing here alpha by alpha over 2, we get the desired formula. Sine of alpha over 2 equals plus minus 1 minus cosine squared alpha over 2. So that proves this formula. The other two, of course, can be obtained the same way from their analogs on the previous page. All right, let's look at the numerical examples on the next page. And the first example here is asking us to find sine of 15 degrees. So the idea is the following. We're going to find sine squared of 15 degrees first. Using the reduction formulas and using our knowledge of sine of 30 degrees. So the reduction formula I'm going to use is that sine squared equals 1 minus cosine of double angle over 2. So in my situation here, sine squared of 15 degrees equals 1 minus cosine of twice 15 degrees over 2. That's the reduction formula. And the rest is a boring computation because now we know that we're computing cosine of 30 degrees. And that we know is root 3 over 2. And so multiplying by 2 the numerator and the denominator, we get 2 minus square root 3 over 4. That number, by the way, is greater than 0 because root 3 is less than 2, of course. From here, we can find that sine 15 degrees is plus or minus square root of 2 minus root 3 over 4. And now we need to decide whether it's plus or minus. Of course, we understand that 15 degrees is in quadrant 2. Excuse me, quadrant 1. So sine 15 degrees, therefore, is a positive number. And so we should take the positive sign here. And so it will be a root of 2 minus root 3 over 2. I would like to point out your attention to the fact that we have already computed sine of 15 degrees once. Let me get back to that computation. That was our answer. For sine of 15 degrees. And that seemingly is a different number. So the question we should immediately ask is this the same number as root 6 minus root 2 over 4? Surprisingly, yes. And you can easily check that. You can easily check that. So we are verifying whether root 2 minus root 3 over 2 equals root 6 minus root 2 over 4. Well, multiply both sides by 4. That'll give you 2 root 2 minus root 3 and root 6 minus root 2. Square up both sides. It'll give us 4 2 minus root 3, 6 plus 2, square of one guy plus square of the other guy, minus twice their product. 6 times 2 is 12. So we have, if we distribute the 4 on the left side, 8 minus 4 root 3 versus 8 minus 2 root 12. So that's, of course, negative 4 root 3 versus negative 2 root 12. Cancel negative 2's. So now we're comparing 2 root 3 versus root 12. Well, root 12, which is of course root of 4 times 3, is indeed 2 root 3. So we have equality here everywhere. And in fact, this isn't a new answer. This is the same answer as we had in the past. All right, for the next problem, let me add a new page. We need to compute sine, cosine, and tangent of alpha over 2, given that tangent alpha is known and alpha lies in quadrant 3. So the idea is this. Let's first draw this situation using the unit circle. So tangent is 8/15. So say this is the angle. This is the angle, yes, whose tangent is 8/15, one of them. But our angle alpha actually is in quadrant 3. So we need this angle. So before we find sine, cosine, and tangent of the half argument, maybe we should first find sine and cosine of the single argument of just alpha. So the idea is this. First, find sine alpha and cosine alpha. Not sine and cosine of alpha/2, just of alpha. And then use the reduction formulas to find sine alpha/2 and cosine alpha/2. All right, can we find sine and cosine alpha from the information we know? Well, let's look at the unit circle. So we have here the tangent of alpha equals 8/15. Let this angle be alpha prime. And of course, the connection between them is that alpha equals alpha prime plus pi. So therefore, tangent alpha being tangent of alpha prime plus pi by the fact that tangent is a pi periodic function, also is 8/15. Now, in this right triangle, let's write tangent alpha prime as opposite leg over adjacent leg. Adjacent leg we know is 1. So opposite leg is therefore 8/15. This distance is 8/15. And now if we look at this triangle, where we know this side is cosine alpha prime, and this side is sine alpha prime. We know their ratio. Sine of alpha prime over cosine alpha prime is 8/15. So we have that tangent of alpha prime being sine of alpha prime over cosine of alpha prime is 8/15. We can now try to solve this equation by raising both sides into the second power and noting that sine squared alpha prime over cosine squared alpha prime equals 8/15 squared. That's 64/2225. And now we can replace, for instance, cosine squared in the denominator by sine squared. We can view this as an equation in sine alpha. I can now set sine alpha to be, say, t. So my equation is now t squared over 1 over t squared equals 64/2225. We need some algebra here. So we get 225 t squared equals 64, 1 minus t squared. Distributing 64, we get 64 minus 64 t squared. And on the left, we get 225 plus 64 t squared equals 64. And 225 plus 64 is 289. And so from here, t squared equals 64/289. From here, t equals plus minus square root of 64/289. And 289 is the square of 17, so we get plus minus 8/17. Because alpha prime is an angle in the first quadrant, sine alpha prime will be positive. So we conclude that sine alpha prime is positive, 8/17. We can now easily find cosine alpha prime. That is, of course, positive, because again, alpha prime is in the first quadrant. Square root 1 minus sine squared alpha prime. That is square root of 1 minus 18/17 squared. After some algebra, we get 1 minus 64 over 289. And that we know will be 289 minus 64 over 289. That in turn equals square root of 225 over 289. And that is simply 15 over 17. So again, sine alpha prime is positive 18 over 17, and cosine of alpha prime is positive 15 over 17. Our knowledge of sine and cosine of alpha prime immediately gives us sine and cosine of alpha, because alpha and alpha prime are only different by half revolution pi. Cosine alpha being cosine of alpha prime plus pi simply is negative cosine alpha prime, and so cosine alpha is negative 15 over 17. Which makes sense because alpha is an angle in the third quadrant. Cosine and sine are expected to be negative. Now we can do the same thing with sine alpha. That's alpha prime plus pi. And of course, that's negative sine alpha prime. So sine alpha is negative 18 over 17. Now, following our idea, once we know sine alpha and cosine alpha, we use the reduction formulas. We know, for instance, that sine squared of alpha over 2 is 1 minus cosine of twice alpha over 2 over 2, which is 1 minus cosine alpha over 2. And in our situation, that is 1 minus negative 15 over 17 over 2. So that's 1 plus 15 over 17 over 2. 15 plus 17, that's 32 over 2 times 17. Canceling 2 and 32, we get 16 over 17. And the same work for cosine squared alpha over 2. By the reduction formula, so the formulas we are using are these ones. We could have used these formulas, but they're pretty much the same as these ones. So these two formulas is what I'm using. So we get 1 plus cosine of twice alpha over 2. So that is 1 plus cosine alpha over 2. 1 plus negative 15 over 17. Seventeen minus 15 is 2. So we get 2 over 2 times 17, which is of course 1 over 17. Now we need to understand the quadrant in which alpha over 2 is before we take square roots. Well, the argument is this. Since alpha is in quadrant 3, that means that alpha is between pi and 3 pi over 2, but that is equivalent to alpha over 2 being between pi over 2 and 3 pi over 4. So in other words, alpha over 2 is in quadrant 2. And therefore, sine of alpha over 2 is positive, and cosine of alpha over 2 is negative. Therefore, sine of alpha over 2 is the positive square root of 16 over 17. It's 4 over root 17. Or if you wish, 4 root 17 over 17. And cosine of alpha over 2 is the negative root of 1 over 17. That is negative root 17 over 17. And therefore, the tangent of alpha over 2 is simply the ratio of these two, four over root 17 over negative 1 over root 17. That is simply negative 4. This finishes this example. The next round of formulas are identities that allow you to transform products of trigonometric functions into sums and differences, and vice versa. Sums of trigonometric functions into products. So how do we derive them? Well, the idea is to recall the corresponding formulas for the sine and cosine of sums and differences. Say, if we recall the formula for sine of a sum and sine of a difference, and add these two equations or subtract them. What we get is that sine of a sum plus sine of a difference equals the sum of the right-hand sides, which is sine alpha cosine beta plus cosine alpha sine beta plus sine alpha cosine beta minus cosine alpha sine beta. And clearly, there are terms that cancel out, cosine alpha sine beta. These terms are identical. Combining them, we get 2 sine alpha cosine beta. And from here, we get that sine alpha cosine beta equals 1/2 sine of a sum plus sine of a difference. Pretty much the same idea here. When we subtract these two equations, we get that sine of a difference, sine of a sum, excuse me, minus sine of a difference equals sine alpha cosine beta plus cosine alpha sine beta minus sine alpha cosine beta plus cosine alpha sine beta. This time we also have two terms that cancel out, sine alpha cosine beta, and the other two terms are identical. So we simply get 2 cosine alpha sine beta. So from here immediately, cosine alpha sine beta is half the sum, half the difference, sine of a sum minus sine of a difference. And of course, the same goes for the formulas for cosine of a sum and cosine of a difference. If we write cosine of a sum, and cosine of a difference, and as before, add or subtract them. As a sum, we get the following thing. This time we have sine alpha sine beta canceling out, and the other two terms are identical, cosine alpha cosine beta. So that is simply twice cosine alpha cosine beta And from here, cosine alpha cosine beta is half the sum cosine alpha plus beta cosine alpha minus beta. Or if we subtract these two things, we get the difference cosine alpha plus beta minus cosine alpha minus beta equals cosine alpha cosine beta minus sine alpha sine beta plus cosine alpha cosine beta plus sine alpha sine beta. I'm subtracting them, so I should get here negative and also negative here. So cosine alpha cosine beta cancel out, and the other two terms are again identical. So from here, if we divide sine alpha sine beta, combining them, I get negative 2 sine alpha sine beta, and dividing by negative 2, I get that sine alpha sine beta equals 1/2. Since I'm dividing by negative 2, I need to reverse these two. It will be cosine alpha minus beta minus cosine alpha plus beta. And we can see, if we have all these four formulas above, product of cosines, for instance, equals half the sum. That's formula 1. Product of sines is half cosine of a difference minus cosine of a sum. That's formula 2. This here is formula 3. And this here is formula 4. We have all four of them proved. All right. Now, formulas that turn sums to products are also very useful, especially in calculus, in various proofs. So what we should do to prove them is simply take the formulas we have here and in each of these formulas we should set alpha to be x plus y, or rather, let's see, x to be x plus beta over 2 and y to be alpha minus beta over 2. From here it's easy to find alpha and beta expressed through x and y. Alpha from here is half the sum, correct? If x is alpha plus beta over 2 and y is alpha minus beta over 2. If I add them, I get that x plus y equals alpha over 2 plus beta over 2 plus alpha over 2 minus beta over 2. Alpha over 2 plus alpha over 2 is alpha. So alpha is x plus y, and if we subtract them, x minus y, we get alpha over 2 plus beta over 2 minus alpha over 2 plus beta over 2. This time it's beta. So alpha is x plus y, and beta is x minus y. So what we get in these formulas, say from this one, is that sine alpha, which is x plus y, times cosine beta, which is cosine of x minus y, equals 1/2 sine of alpha plus beta, which is x, plus sine of alpha minus beta, which is y, equals sine alpha plus beta. All right, so what is alpha plus beta? Alpha is x plus y, beta is x minus y. Alpha plus beta is x plus y plus x minus y. So that's simply 2x. Let's see if this is correct. So I want to take this formula and if I set alpha to be x plus y over 2 and beta to be x minus y over 2. So from here, maybe a little different. Yes, if I now solve this for x, for instance, x is adding these two, x over 2 plus x over 2. That's x, that's alpha plus beta. And y will be alpha minus beta. Let's see if that will give me the right thing. So in this formula, I set alpha to be x plus y over 2 and beta to be x minus y over 2. So the left-hand side, sine alpha, becomes sine of x plus y over 2, that's alpha, times cosine beta, that's x minus y over 2, equals 1/2 Sine of alpha plus beta. Well, alpha plus beta is x. And alpha minus beta, that's y. In other words, if we multiply this by 2, sine x plus sine y equals 2 sine x plus y over 2 cosine of x minus y over 2. That is this formula. So I should say that x is alpha plus beta, that x is alpha plus beta, not over 2. And y is alpha minus beta. So in short, I'm simply plugging into these formulas, specific alpha and beta, with alpha being x plus y over 2, beta being x minus y over 2. If I now do this with this formula, I will get that cosine alpha, which is x plus y over 2 times sine beta, which is x minus y over 2, with this being alpha, this being beta, equals 1/2 sine alpha plus beta, which is x, minus sine alpha minus beta, which is y. So from here we get, multiplying by 2, that sine x minus sine y equals twice cosine of x plus y over 2 sine of x minus y over 2. That is this formula. This formula is especially useful in calculus when you need to prove that sine is a continuous function. And the same thing with the other two formulas. If I copy paste these two formulas, and again use my substitution, so take this formula and instead of alpha and beta write x plus y over 2, x minus y over 2. So we will get cosine alpha, that's cosine of x plus y over 2, cosine beta. Beta is x minus y over 2. That's alpha, that's beta. Equals 1/2 cosine of alpha plus beta, that's x, plus cosine alpha minus beta, that's y. From here we get that cosine x plus cosine y equals twice cosine of x plus y over 2 cosine x minus y over 2. That is this formula. And finally, the same trick with the last formula. If I replace alpha by x plus y over 2, and beta by x minus y over 2, I get, according to this formula, 1/2 cosine of alpha minus beta. That's y. Minus cosine of alpha plus beta. That's x. So from here, if I multiply this by -2, cosine x minus cosine y equals -2 sine x plus y over 2 sine x minus y over 2. That is this formula. So these formulas are consequences of the formulas on the previous page, and these formulas are simply manipulations, were obtained by manipulations with the formulas for sine and cosine of sums and differences. All right, let's now work with a couple of numerical examples. In this first example, we need to evaluate cosine of 11 pi over 2 times cosine of pi over 2. We note immediately that the sum of these two angles, 11 pi over 2 plus pi over 2 over 12, is of course 12 pi over 12, which is pi, and we know all trigonometric functions of pi, and also the difference, 11 pi over 12 minus pi over 12, being 10 pi over 12, simply is 5 pi over 6. And again, we know trigonometric functions of 5 pi over 6. So it makes it a good idea to apply the product to sum formula, because we will need to compute trigonometric functions of pi and 5 pi over 6, which is easy. So applying the product to sum formula, which one? This is a product of cosines. We need this formula, product of cosines. So let me write it here, product of cosines, cosine alpha cosine beta equals 1/2, have the difference, sine of a sum, minus sine of a difference. All right, so if we apply this formula here, we will get 1/2 cosine of sine of a sum. Just to check again, we have here product of cosines. Product of cosines, excuse me, I copied the wrong formula. This is product of cosines here. So we need 1/2 sum of cosines. So this will be 1/2 cosine of a sum, 11 pi over 12 plus pi over 12, plus cosine of a difference. Eleven pi over 12 minus pi over 12. Note, by the way, that this formula is symmetric in the sense that if you were to flip here in this formula alpha and beta and write this as cosine beta cosine alpha, this would be 1/2 cosine beta plus alpha plus cosine beta minus alpha. And of course, this and this are equal, and this are equal. The question is, why are this and this equal? Well, cosine of alpha minus beta and cosine beta minus alpha are equal because cosine is an even function, and so when I write cosine alpha minus beta, if I factor out the minus, so that in parentheses I have beta minus alpha, I can ignore the minus, and this simply becomes cosine beta minus alpha, since cosine is even. All right, so if I continue here, after applying the above product to sum formula, we get 1/2 cosine of pi plus cosine of 5 pi over 6. Now cosine of pi we know is -1. What is cosine of 5 pi over 6? Well, we can remind ourselves by drawing the unit circle. Here is the angle 5 pi over 6. And we see that cosine of 5 pi over 6 is simply negative of cosine of pi over 6. because the reference angle for 5 pi over 6, of course, is pi over 6. These 2 points have equal y coordinates but opposite x coordinates. So cosine of 5 pi over 6 simply is negative cosine of pi over 6, and cosine of pi over 6 we know is negative root 3 over 2. So this here becomes 1/2 negative 1 plus or minus root 3 over 2, and some algebra here. So we get negative 1/2 minus root 3 over 4, and that is negative root 3 plus 2, I believe. Okay. Note that, by the way, this number is by absolute value less or equal than 1, because it's a product of two numbers, each by absolute value less than 1. And indeed, you can check this number belongs to the interval negative 1, 1. Again, absolute value of this number being the product of absolute values of two cosines cannot be more than 1, because each of them is no more than 1. All right, that was the first problem. And in the second problem, when we need to evaluate cosine of 15 degrees minus cosine of 75 degrees, we could in principle use our computations from before we once computed 15 degrees, cosine of 15 degrees and cosine of 75 degrees, but it's actually easier. Here we don't need to compute them separately, because we note that these two numbers, 15 degrees and 75 degrees, add up to 90 degrees. And also the difference of them, 15 minus 75, is negative 45 degrees. Excuse me, negative 60 degrees. So it will be very convenient to transform this difference to a product. It makes sense to use one of the sum to difference for sum to product formulas. Because when we use them, whenever you use a sum to product formula, you will have to work with have the difference and have the product. Have the difference and have the sum of your arguments. Have the difference will be half of negative 60, which is negative 30. And have the sum is also very convenient, because that's just 45 degrees. And computing trigonometric functions of 45 degrees or negative 30 degrees is very convenient. So which formula should we use? We have here difference of two cosines. That is this formula. So the formula is cosine x minus cosine y equals negative 2 sine of half a sum sine half the difference. So by this formula, cosine of 15 degrees minus cosine of 75 degrees will be negative 2 sine of half the sum, 15 plus 75 over 2, times sine of half the difference, so 15 minus 75 degrees over 2. We have applied the formula. Now a little algebra here. We get negative 2 sine of 45 degrees. That's 15 plus 75 over 2 times sine of negative 30 degrees. Well, we can transform this further. Sine of 45 degrees is root 2 over 2. This here, we can use the fact that sine is an odd function. And so the minus goes outside to give us negative sine of 30 degrees. 2 and 2 cancel out. Negative and negative cancel out. We get root 2 times sine of 30, which we know is 1/2. All right, this example is now over, and we are done with our study of trigonometric identities. Thank you.